biographical information. David got his undergraduate degree at MIT. While he was at MIT, he traded Cambridge, Massachusetts for Cambridge, England for a year, I believe to escape the infamous MIT Junior Lab. I don't think there was any other purpose of doing that, but I'm not sure. David went to Berkeley for his PhD, where he worked on, among other things, granular theories and dark matter. And from Berkeley, he went to Harvard and the Institute for Advanced Studies, where he turned his attention to conformal bootstrap, which is the subject of his talk today. David arrived at Yale, I believe, in 2012, and has won a number of awards, including the NSF Career Award and the Arthur Greer Memorial Prize, and was a member of a fairly large play theory standards collaboration called Simon's Conformal Bootstrap Collaboration. So turning to today's talk, it's titled Islands in the Conformal Sea. If you feel like your geography is a bit rusty because you cannot point to the conformal sea on the map, I assure you that neither can Google AI. Google AI gave a number of hilarious or seemingly bogus explanations for what the conformal sea might be. And I won't list all of them, but it involved a paint for marine electronics and mapping the ocean sea. So for the true answer about conformal sea, let us turn to David and see what he has to say.
All right, thank you, Vitek. So it's my great pleasure to be giving today's physics club. I'm going to tell you something about the conformal bootstrap, and hopefully I can convey to you today a sense of first of all, what these words mean, and what kind of physics they connect to, and also a sense of why this research program has been and continues to be extremely exciting. Now, as you can tell from the title of my talk, in this field, people have kind of latched on to nautical metaphors. And so there are islands and seas and navigating and archipelagos. And you'll get a sense for why these words started cropping into the nomenclature. But it also kind of highlights that there's really no better place to start in discussing this business than to start with water. So I'm going to start with water. And as everyone knows, as you vary its temperature and vary its pressure, water has different phases. What I'm going to hone in on is that there's a nice line separating the liquid and vapor phases. And if you keep tracking this line, go to higher temperatures, higher pressures, eventually you'll see that it ends at a point called a critical point. And in some sense, what one perspective on my talk today is that it's going to be asking the question, well, what happens at the critical point? What happens when we go there and explore it? And I have to warn you, this is a real rabbit hole that you can jump into and get sucked into and then start spending your career trying to answer this question. Let's get started. Let's see where we go. Experimentally, it's a bit hard to do with water, but you can take other fluids and take them near their critical points. And what you see is that if you get close enough to the critical point, you see a phenomenon called critical opalescence. Okay, a fluid which is ordinarily clear becomes kind of milky white as you get close to its critical point. And light has trouble passing through. Now, why is that? Physically what's happening is you can think about thermal fluctuations of the fluid. And these fluctuations happen over longer and longer distance scales as you approach the critical point. Quantitatively, this can be measured by something called a two-point correlation function. You ask how correlated is a density fluctuation here with a density fluctuation over here. If their points are far enough apart, then the fluctuations are basically uncorrelated, and you'll see an exponential fall-off in the two-point correlation function. If the points are close together, you can instead see that they're very correlated with each other, and the correlation follows some kind of power law behavior. And that power law is characterized by an exponent, which is often called eta. Now, the separation between these two regimes, power law at short distances, exponential fall-off at long distances, is characterized by a scale called the correlation length. And what happens as you approach the critical point is that the correlation length gets longer and longer. You see these power law correlations over longer and longer distance scales. And at some point, the correlation length gets comparable to the wavelength of visible light. That's what leads to critical opalescence. These fluctuations start interfering with the ability of light to pass through. But then if you keep going, you can get even closer, you see the correlation length start to diverge, kind of goes off to infinity. And the way it goes off to infinity itself follows a power law. It goes like the temperature minus the critical temperature to some other power, minus nu. And so the key point here is that as you get close enough to the critical point, what you see are some power law behaviors that are characterized by exponents. And these exponents really encode the physical properties of the fluid near this critical point. Now, something really kind of amazing and cool is that you can look at lots of different fluids, try to measure their critical exponents as you go to their critical points, and you always see the same numbers popping out. Okay, so you can look at hydrogen, carbon dioxide, ethane, nitrogen, and so on. You measure the critical exponents. Here I'm plotting beta, which is some particular combination of nu and eta that's easy to measure. It describes the power law behavior of the order parameter. But there's it's clear that there's some kind of universal structure that's governing the behavior of all these different critical points. It gets even more interesting because there are completely different kinds of physical systems. Magnets made out of rare earth metals, binary fluid mixtures, even certain quantum critical points that all show the same exponents. And so there's some real kind of universal mathematical structure that's popping up in lots of different physical systems that's worth understanding. This is sometimes called universality. Now, okay, so now we have this real kind of interesting observation and perhaps puzzle. You know, how is it that boiling water can have the same properties as a magnet? Okay. Well, we can get a clue by thinking about the fact that this correlation length is diverging, going off to infinity, and it's really pointing to the fact that kind of physical length scales are disappearing from our system. We're left with power laws. Power laws look the same at all scales. If I zoom in on a power law, it still looks like a power law. So this is really a clue that there's some kind of emergent scale invariance in these systems. In fact, it's believed that the symmetry is enhanced to an even larger group called the conformal group. Now, what is the conformal group? Well, it consists of several different transformations, some of which you're familiar with and some of which are a little bit weird. The conformal group consists of translations, moving from here to here, rotations, rescaling, zooming in and out. Also some funny things called special conformal transformations, which are ways of twisting space in a way that preserves angles. So here I have a grid of points where all the lines intersect each other at 90-degree angles, and then I'm twisting that grid in a way where they still intersect each other at 90-degree angles. That's an example of a special conformal transformation. And it's believed that that's an emergent symmetry, which shows up at these critical points. Now, if you get nothing else from this talk, I want you to just meditate for a moment on the statement that there's a beautiful scale-invariant structure hidden inside of boiling water. Okay, I find this very inspirational. And it's really pointing to some kind of deeper beauty of nature that we can all contemplate.
You'd have to have pretty high temperature, high pressure in your kitchen to actually be putting.
You would, that's true. That's true. You need a very fancy kitchen. All right. Now, okay. So now, what can we say about this structure? So the structure is generally called a conformal field theory, and I told you these structures have this symmetry, conformal symmetry, and that symmetry allows you to kind of organize your thinking. Okay, you can think about the fields describing your system, like the fluid density. More generally, they're called local operators. These are different ways of perturbing your system in a local way. And you can kind of organize those local operators according to how they behave under different conformal transformations, like rescalings, rotations, special conformal transformations, and so on. So for example, if I take a local operator and I zoom in, so I take x to lambda times x, then that operator might respond by getting multiplied by lambda to some power minus delta. Okay? Here we say that the scaling dimension of the operator O is delta. This is kind of a fancy version of what we do when we do dimensional analysis. Okay? So if you say change your units from meters to kilometers, then areas will transform in a different way as lengths. Okay? This is just telling us that different local operators transform in different ways when you zoom in or zoom out. Now, the key point here is that the scaling dimensions of these operators are directly related to the critical exponents that you see in experiments describing these power law behaviors. Okay, so there's one local operator, sigma, whose scaling dimension is related to the exponent eta. There's another local operator, epsilon, whose scaling dimension is related to nu, and so on. In fact, in general, there's an infinite number of operators, an infinite number of ways of perturbing your system that all have a rich spectrum. Okay, so there's a mathematically very interesting spectrum of scaling dimensions to think about. One thing that's worth keeping in mind is that the number of so-called relevant operators, these are operators with the scaling dimension smaller than the space-time dimension, d, is very important because the number of relevant operators controls how many parameters need to be tuned in your system in order to reach the critical point. Yes, Jack?
Since you gave the example of water at the critical point, could you say what sigma and epsilon actually are?
Yeah, so in the case of water or other fluids, this field sigma would correspond to density perturbations. Okay, fluctuations of the density around its average value. Okay, epsilon is like changing the temperature. Okay, so these are kind of two different ways of perturbing your system, and you can look at the response to those perturbations and then see some power law behavior as a response. Okay. So the fact, going back to water, so the fact that the phase diagram of water is two-dimensional, we need to tune the temperature and tune the pressure in order to reach the critical point, is immediately telling you that in the conformal field theory describing that critical point, there's two relevant operators. Okay? So there's this direct connection between the properties of this spectrum of scaling dimensions and kind of the macroscopic properties in the vicinity of our critical point. Okay, so what is this conformal field theory? Well, it has a name. The conformal field theory describing liquid vapor critical points as well as uniaxial magnets is often called the critical three-dimensional Ising model. Typically, the Ising model is realized using a system of interacting spins. So I can have a lattice of spins which can point up or point down. They could have some nearest neighbor interactions with some interaction strength J. And then you could tune this interaction strength to find a critical point. Now, you may recognize this image as being from a gate, which is about a block north on Prospect Street. If you don't, I encourage you to go visit this gate. And this is because the two-dimensional Ising model was famously solved here at Yale by Lars Onsager in 1944. On the other hand, the three-dimensional Ising model has never been solved. It's been kind of this enigma that people have kind of fought and battled for many decades. Now, there are different ways to approach this Ising critical point. One way to do it is to take the continuum limit of this picture of interacting spins. And then instead of this lattice of spins, you can talk about a scalar field, sigma of x, which describes the density of the spins. And you can write down a Lagrangian. for that spin density. It has a kinetic term, it has a mass term, it has some self-interactions, lambda, and so on. In this continuum formulation, where I have a field which can evolve, it still has a critical point. You can tune these parameters such that the excitations of the system are gapless, and it has scale invariance and conformal invariance, and so on. But at that critical point, there's kind of no sense in which this theory is weakly coupled, or you could use perturbation theory, or you could do a Taylor expansion in any parameter. Okay, so we kind of know how to, one way to approach the critical point, but it's strongly coupled, and it's very hard to figure out how you actually calculate anything about it. Of course, there's a long history of people trying to do this. There are various methods people have come up with. The epsilon expansion, high temperature, low temperature expansions, large N expansions. But this is really a place where the method that I'm going to talk about really shines. So I'm going to tell you about the conformal bootstrap. This comes from the phrase of pulling yourself up by your bootstraps. I don't know if anyone's tried to do that before, but it's not so easy. Really, what it asks you is, how far can you get using what you have on you, or mathematical consistency of your theory? Okay, use the things that you know to see how far you can get. And more concretely, the conformal bootstrap tries to use positivity properties of correlation functions combined together with all the symmetries of your system, like conformal symmetry, other global symmetries, constraints called crossing symmetry. You put all these together and hope that together they're strong enough to let you solve, or at least tightly constrain, these strongly coupled systems. Now, that might sound like a foolish dream, but actually it had a nice success story. So the conformal bootstrap idea kind of originated in the 70s, following up on an earlier idea called the S-matrix bootstrap, and then had a beautiful success story in the early 80s, when Belevin, Polyakov, and Zamolodchikov used conformal bootstrap methods to exactly solve and classify a class of two-dimensional conformal field theories called the minimal models. The 2D Ising model is one of the simplest versions of this. And so, for example, they were able to use bootstrap methods to exactly determine that the scaling dimension of sigma is 1/8, and the scaling dimension of epsilon is 1 in the critical 2D Ising model. Now, in higher dimensions, like 3 dimensions, progress has been much slower. And it wasn't until kind of 2008 that it got revitalized and the idea picked up again, in part because of some new ideas and in part because of throwing modern computing technology at the problem. So how does it work? Well, so now I'm going to get into the weeds a little bit just to show you, give you a sense of how this operates. So what you do is you think not about 2-point correlation functions, which I mentioned before, but you think about 4-point correlation functions. Okay, so how correlated is an excitation here with excitations here, here, and here? Okay, that's kind of a complicated object. But one of the nice things about 4-point correlation functions is that they can be expanded in a way which really probes the spectrum of your theory. Okay, so they can be expanded in a basis of functions called conformal blocks, G delta L. And these blocks are like special functions that capture the contribution of some operator in your theory to the 4-point function. They're characterized by the scaling dimension delta and the spin L, or angular momentum of that operator. And this is kind of similar to doing, taking a function and expanding it in spherical harmonics. These conformal blocks are like harmonics of the conformal group. And you can always do this expansion. Now I could give a completely different talk, or really series of talks, on how these conformal blocks are computed. There's a lot that goes into it. They satisfy some differential equations. They satisfy some recursion relations. They have a beautiful analytical structure as a function of delta. You can expand them in series expansions if you choose the right coordinates, and so on. I'm going to sweep all that under the rug, but a lot of effort in recent years has gone into figuring out efficient ways of computing these conformal blocks, and now there's some very nice software packages that will do it for you. Okay, so now we're not done. So I told you we can expand the 4-point function in conformal blocks. By the way, there are some coefficients in this expansion as well. I wrote it as lambda sigma sigma O squared. These lambdas are kind of unknown coefficients that characterize the 3-point functions in your CFT between sigma, sigma, and O. And the key point here is that the squares of those coefficients show up. So the coefficient in front of the conformal blocks is positive because we can work in a basis where these lambdas are real numbers. Now we're not done yet. So we have this 4-point function. We can expand it in blocks, but it's also an object which is symmetric under permutations of different points. So for example, I could exchange x1 with x3, and it should be invariant. It should equal itself under that exchange. Now, this symmetry under exchanging x1 with x3 is not kind of manifest in this conformal block expansion, and it actually tells you that one expansion in conformal blocks should equal another expansion in conformal blocks. This is sometimes called crossing symmetry. If I want, I can kind of put both terms on the same side of the equation and write it as a sum rule. A sum over differences in blocks with positive coefficients has to equal 0. This is really kind of one of the simplest versions of a bootstrap equation. Here the unknowns are the scaling dimensions, delta, the coefficients, which are related to 3-point function coefficients in the CFT. And then we also have some positivity properties. The coefficients lambda squared are positive. There are also some positivity properties on the scaling dimensions. They have to be bigger than some minimal value called unitarity bounds, which is ultimately related to some positivity properties of 2-point functions. You want to make sure that all 2-point functions are positive. Okay, so now we have a sum of some functions with positive coefficients has to equal 0. Now, when is that possible? Okay, when can I sum up a bunch of functions with positive coefficients and get 0? Well, think of these functions as being like vectors. Okay, when can you sum up a bunch of vectors with positive coefficients and get 0? You can do it if you're in a situation like the left, where all the vectors point in different directions, and you can kind of balance them against each other to get the 0 vector. You can't do it if you're in a situation like the right, where all the vectors point to one side of some plane. Okay, then if you sum up these vectors with positive coefficients, you'll always have some component orthogonal to the plane. So what we really want to know is, are we in a situation like this, or are we in a situation like this? And so that's kind of what we do with the bootstrap numerically. We ask, does there exist some kind of separating plane that puts all these functions to one side of it in the appropriate sense? Concretely, we look for linear combinations of derivatives that we could apply to the crossing equation that have nice positivity properties. And what we try to do is make some assumption about the spectrum, make some assumption about the deltas and the lambdas. These were the unknowns in our problem. And then try to apply some derivatives to the crossing equation and prove that -1 equals a sum of positive contributions. If we can show that we can find some linear combination of derivatives that implies -1 equals a sum of positive contributions, then we have a contradiction. Okay? So whatever assumption we made, we then conclude is incompatible with crossing symmetry and unitarity or positivity. So that's the basic strategy. We make an assumption, try to prove a contradiction. Now, how do we find this alpha, or this linear combination of derivatives? Well, this can be formulated numerically as a kind of convex optimization problem. Concretely, there's a class of optimization problems called semi-definite programs. These are optimization problems involving constraints that involve positive semi-definite matrices. There's kind of a lot of literature about solving these semi-definite programs. There are well-known interior point algorithms for finding their solutions. There's a nice piece of software called SDPB, which was developed to solve semi-definite programs with bootstrap applications in mind. And so I don't want to get into the weeds of precisely what these problems look like, but I just wanted to say that kind of simple computations here, can be done very quickly. They can take seconds on a laptop. The most intense computations, you really push things far. You have a very large search space. You look at lots of crossing equations simultaneously. These can take millions of core hours on high-performance computing clusters. Okay, so there's a whole range of what you can do depending on how much computing time you're willing to throw at the problem. There's also a very nice software repository of software for setting up bootstrap problems, rewriting them in the form of semi-definite programs, which has been developed by this bootstrap collaboration that Vitek mentioned, and you can find a lot of that software here. Okay, so I like this cartoon because it has many layers of meaning, but on its surface, it tells you that if you try to pull yourself up by your bootstraps, you're chained to inequalities. Okay, we have inequalities entering our problem. We're led to inequalities on CFT data, and it's also very hard to do this because you sweat a lot when you're trying to compute these inequalities. Okay, so here's an example of an inequality or bound coming from the conformal bootstrap. You look at 4-point functions of sigma and ask what is the upper bound on the scaling dimension of the first operator epsilon that contributes to its 4-point function. Out here in the disallowed region, what it means is that you're able to find this separating plane. You're able to find this linear functional which proves or implies a contradiction. And so everything out here is basically rigorously ruled out. Everything in the allowed region is not ruled out. So there could be theories living here, but you don't know for sure whether they are. This bound is essentially a rigorous bound and gets stronger and stronger as you throw kind of more computing power at it, as you have a larger and larger search space for these functionals. Okay, so of course, one thing immediately jumps out about this bound is that there's a very kind of prominent change in slope. And so it's kind of a really amazing observation, this really didn't have to happen, that the location of this change in slope, or this kink, coincides very precisely with the known data of the critical three-dimensional Ising model. So we know this data, as I mentioned, from experimental measurements. We also know it from precise lattice simulations. So for example, delta sigma is about 0.518, delta epsilon is 1.412, and that's precisely matches to the location of this kink. Okay, this raises a lot of questions. Okay, why in the world did this theory, we computed a completely general bound on three-dimensional conformal field theories. Why does this one theory that we know about live on the boundary, live in some kind of special kink? It's really kind of calling out for a deeper explanation, which we're still thinking about, I would say. We've learned a lot.
David?
Yes?
So every point on the line of the kink is a possible critical point?
Every point in this allowed region is a possible critical point. So that includes on the boundary as well. We haven't thrown all possible constraints into the system. Okay, so there are more constraints coming from, this is just coming from one 4-point function. So there are more constraints coming from other 4-point functions. And those might rule out some of this allowed region. Yes?
How did the three-dimensionality enter into this analysis, David?
The three-dimensionality entered by using the conformal blocks for three-dimensional CFTs. it also enters in the form of the unitarity bounds on the scaling dimensions. Those are dimension dependent. But it's kind of, it's pretty easy to change dimensions in the bootstrap. Okay, doing this computation in 100 dimensions is just as easy as doing it in 3 dimensions. You just have to use a different form for the blocks and different constraints. So it's very different, has a very different status than like lattice computations, which get much harder as you increase dimension.
2 dimensions would be a bit different.
Yeah, 2 dimensions is different. Of course, you could do the analog of this analysis in 2 dimensions where you just use the global conformal group, but you also have more powerful tools at your disposal because you can use the Virasoro algebra structure to write down a more powerful set of bootstrap equations. Yes?
3D model is a model where formula is easy to write down. But that's not the reason it's singled out in the diagram, right? Any other properties that, other than the fact where it is distributed?
Sorry, say the question again?
Right? The actual Ising model.
Yeah.
If you move a little bit to the right, it's another physical model.
Yeah, good question. So for example, so the answer is yes. There is a kind of a continuous way to deform the 3D Ising model. And in fact, there's a family of what are called long-range Ising models. These are like a particular kind of non-local deformation of this model, which is still allowed by these bounds. So that's an interesting story. And it also relates to what I'm going to say next. So, yes.
Use the Ising Z2 symmetry.
Yes. Yes. So this did use the Z2 symmetry because we assumed that the leading scalar operator in the sigma sigma OPE was epsilon and not sigma. Okay. Other questions? Okay, so we can go farther by not just looking at a single 4-point function, but looking at a system of 4-point functions. So here we've now looked at 4-point functions, sigma sigma, epsilon epsilon, epsilon 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 epsilon, and combined that with sigma 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 sigma. So now we have this system of 4-point functions. We've used a Z2 symmetry of sigma, that it's odd under sigma to minus sigma, to avoid writing some of the others. And it turns out that if you use the system of crossing equations that you get from these correlators, along with some very mild physical input, that sigma and epsilon are the only relevant operators, instead of a bound with a kink in it, you actually get some kind of isolated island in parameter space, which is disconnected from some bigger continent over on the right. So this is very exciting. So now we've really kind of isolated this solution. By the way, this also relates to Shankar's question. He was asking if there's other theories which are connected to the Ising model, which go off to the right. And these assumptions that say sigma and epsilon are the only relevant operators actually excludes those other solutions. So that's part of how we get rid of the family of solutions that's connected to the Ising model and are able to isolate it in this space. Well, so now that you have an isolated island, you can make it your mission in life to try to shrink it as much as possible and see how far you can get. So first of all, you can, try to make your search space as big as possible in this system. Go to 1,000-dimensional search space rather than 100-dimensional search space. And that lets you shrink it pretty far. You can actually get it about 2 orders of magnitude smaller than the best Monte Carlo simulations, just from this alone. Actually, this is a little misleading because this island is really a 3-dimensional allowed region. We have to do map out a 3-dimensional space, delta sigma, delta epsilon, and the ratio of their 3-point coefficients. And so this is a projection of that 3-dimensional allowed region that we've mapped out. So that's pretty good. That was the state of the art for a long time. But we've realized that we can take this even farther by bringing a new player into the game, which is an operator called the stress tensor. Okay, so the stress tensor is a very important special operator. Every local conformal field theory contains a stress tensor. It contains the currents associated with all the symmetries of the theory. It tells you how the theory carries energy and momentum. You can give interpretations to its different components. But it's really a kind of nice universal object that exists in all local conformal field theories. And so you can use it to start making a map of the world. Since all theories have one, you can look at 4-point functions of the stress tensor and place bounds on the scaling dimensions of operators that might show up in its expansion in conformal blocks. And so here in this plot, I've assumed that the theory has a parity symmetry, and you can divide operators into parity even operators and parity odd operators. So the x-axis is the scaling dimension of the leading parity even scalar operator or spin zero operator in the theory. The y-axis is the leading parity odd scalar operator or pseudoscalar. And you can see that there's a kind of a very interesting allowed region that gets carved out in this space. And in fact, various known theories live in different corners of this space or along the boundary. Different free theories free scalar lives up here, free fermion lives down here. The critical Ising model, its scaling dimension of epsilon was 1.412, so that's right around here. And so we know that it lives somewhere along this vertical dashed line. That actually seems to coincide with some interesting kink up here and a sharp cliff in the allowed region. And so when we first made this plot, we conjectured that the theory actually lives up in this corner. Prior to this work, basically nothing was known about the scaling dimension of the parity odd scalar in the Ising model. So this is just coming from 4-point functions of the stress tensor. We can now combine this with our scalar operators, our sigma and our epsilon, and look at the big system contained of all 4-point functions involving t, sigma, and epsilon. This is a big endeavor. We've been working on this. We worked on this for about 4 years, trying to get all these constraints together, trying to write down all the tensor structures, trying to impose conservation constraints properly. It's a big effort, but it's paid off. And so the state of the art in the bootstrap now, at least for the Ising model, is that we could combine the sigma, epsilon, and t together, look at all 4-point functions containing these operators. This gives us 30 crossing equations plus some additional constraints instead of 5 in the previous plot. And at the end of the day, we kind of have to search through and map out really a 7-dimensional parameter space containing delta sigma, delta epsilon, sigma, sigma, epsilon coefficient, the epsilon, epsilon, epsilon coefficient, the TT epsilon coefficient, and then 2 more coefficients describing 3-point functions of the stress tensor, NB and NF. There's a lot to say about search strategies. I don't know if you've ever tried to search through a 7-dimensional parameter space, but it's not easy. And so we've had to come up with some very clever search strategies for mapping out the space and deciding which regions are allowed, which regions are disallowed, that I'm happy to tell you about after the talk. At the end of the day, though, we were able to shrink this island by 2 more orders of magnitude by combining it with the constraints of the stress tensor. So it's a very fruitful thing to do. And in addition to that, we get very, very precise data. So we learn delta sigma to 8 decimal places, delta epsilon to 7 decimal places, and we also get very, very precise data for all of these 3-point coupling coefficients, many of which were not known very well prior to this work. Actually, that's not all. So in addition to this kind of CFT data involving the external operators in our system, sigma, epsilon, and t, there's all the exchanged this whole spectrum of exchanged operators. And it turns out that by using the properties of this functional that we're using to rule out various parts of parameter space, we can actually extract estimates of the rest of the spectrum of the theory. So this goes by the name of the extremal functional method. We go to a boundary of our allowed parameter space. We take this alpha, which is some linear combination of derivatives on the boundary, and apply it to this difference of conformal blocks. And then you can look at where this has zeros. It has this beautiful set of zeros. And the locations of the zeros actually tell you about the spectrum of a solution to crossing symmetry that lives on the boundary. So you can extract the locations of those zeros, reconstruct all the coefficients, and get an estimate for what the whole spectrum looks like. Well, this gives you lots of information, lots of data. It tells you about whole trajectories of operators of increasing spin that are fun to think about. And so just to give you a small glimpse at that, here I'm plotting some operators as I increase the spin. And on the x-axis is the twist of the operators. That's dimension minus spin. And you can see that there's this beautiful trajectory of black dots, which nicely approaches some constant value. This is actually very, very interesting because as you go to large spin, you can use various analytical methods to study the bootstrap equations. There's something called the light cone bootstrap. You analyze the bootstrap equations in a limit where points get almost light-like separated from each other. And you can prove analytical statements about the large spin behavior of the spectrum, which, among other things, predicts that you should approach this constant value. Here it is equal to 2 delta sigma. There's even more powerful analytical methods. One of them is called the Lorentzian inversion formula, which actually lets you integrate your 4-point function, or really a discontinuity of your 4-point function across a branch cut in the right way, and lets you predict the form of these curves. And so you can see that there's a beautiful agreement with the kind of analytical predictions using this Lorentzian inversion formula and the numerical data, the black dots, that we've extracted from the extremal spectra of this bootstrap calculation. So this is a really kind of fertile ground for developing analytical methods, comparing them with numerical data, and there's insights going back and forth between these two approaches. So right now we're currently working on, yeah? Yeah. Yeah. So I call this Lorentzian inversion. So this is a method that you'd apply in a Lorentzian theory. But of course, these critical points I'm talking about, like 3D Ising, has a Lorentzian version in 2+1 dimensions, as well as a Euclidean version in 3 dimensions. This Lorentzian version and Euclidean version, they have the same spectrum of operator dimensions. They're kind of analytic continuations of each other. So these Lorentzian methods basically let you say things about the Lorentzian version of the Ising model, but it's also teaching you things about the Euclidean one. Currently we're working on, there's many more trajectories. For example, trajectories involving composite operators built out of 2 stress tensors, and a stress tensor and an epsilon, or stress tensor and sigma. Currently we're working on extracting these trajectories from our big numerical data set, trying to clean out all the noise, and then thinking about how to understand them analytically. Okay. So that was a lot of words about one CFT, and in fact, there's many other interesting theories. There's a whole zoo of conformal field theories out there involving multiple scalars, interacting fermions, gauge or spin-1 fields, theories in lots of different dimensions, theories with supersymmetry, theories with gravitational dual descriptions, Okay, so there's a whole zoo out there. And one of the, kind of more broadly, one of the goals of the Bootstrap program is to try to map out the space of conformal field theories, map out theory space, try to use these Bootstrap methods to maybe classify that space, or perhaps just solve all the theories that are interesting. Okay, so we haven't fully classified the space of, say, 3D CFTs, but we've started producing this map. And so, okay, so one class of theories that we are starting to understand very well are called the 3D ON models. These are like theories of n interacting scalar fields rather than one. And different values of n are interesting. So the n equals 2 model, sometimes called the XY model, describes the superfluid transition in helium-4. There's very precise data taken aboard the space shuttle, looking at the heat capacity of helium-4 across this transition. The n equals 3 model is called the Heisenberg model. It's kind of been the go-to standard model of isotropic ferromagnets. At large n, these models are also nice because they're solvable in a large n expansion. Well, we've been working on this for a while, and by now we have some very precise bootstrap islands for the critical O2 model. In particular, our bootstrap island for the O2 model is kind of very nicely compatible with the most precise Monte Carlo or lattice simulations, which are shown in these boxes. There's been a kind of long-standing discrepancy between those Monte Carlo simulations and the experimental measurements taken aboard the space shuttle, which are shown in these horizontal bands. The bootstrap is kind of nicely agreeing with Monte Carlo, so it's highlighting the fact that the experimental analysis must have underreported their error bars in some way. We've also have a nice bootstrap island for the O3 model, which is also in kind of beautiful agreement with Monte Carlo simulations. Another kind of nice physics result that we could extract out of this is that we could prove that the leading 4-index operator, phi I, phi j, phi k, phi l, in the O3 model is irrelevant. We can place an upper bound on this operator over this island, see that its dimension is smaller than 2.99, which is smaller than 3, and basically have a numerical proof that this Heisenberg fixed point is unstable to cubic deformations or cubic anisotropy. More recently, I've been focusing a lot on models of interacting fermions. And there's lots of interesting CFTs that you can build out of interacting fermions. So some of these go under the name of Gross-Neveu-Yukawa models, where I have n fermions, psi I. They interact through a scalar, through some Yukawa interaction, sigma psi bar psi. That scalar itself might have some self-quartic interaction, lambda. And there are many variations on models of this sort. Okay, they can have different numbers of scalars. They can have different signs in the Yukawa couplings. There's kind of an interesting landscape of these models. But they're interesting to think about because they have a variety of applications. First of all, at large n, you can solve these models in a 1 over n expansion. You have some nice analytical control. At other values of n, like 8 or 16 in my notation, these have various possible experimental applications. So they've been proposed to describe quantum critical points in graphene or multi-layer graphene. They've been proposed to describe critical points in tungsten diselenide, where there's some very interesting experiments going on right now. They've been proposed to describe critical points in D-wave superconductors. So it's very interesting to learn about these theories from the bootstrap perspective. Yes?
Sigma is a real scalar?
Sigma is a real scalar, in the simplest version.
The symmetry ON or UN?
Yeah, so there are different models. In the one that I've written down here, these are two-component real scalars, Majorana fermions. Sorry, two-component real fermions. They're Majorana fermions, and there would be an ON symmetry rotating them.
These examples are the same.
depending on which example you're talking about, there might be some variation of this model that's relevant. So I'm not, yeah. But for example, for this model with an ON symmetry and Majorana fermions, that's shown up in a proposed quantum critical point that could appear in D-wave superconductors to describe a time reversal symmetry breaking transition. This is in one of Subir's papers. Okay, at smaller values of n, there's also kind of concrete realizations of these models in lattice or quantum Monte Carlo simulations. So it's kind of a nice arena where there are different methods converging together, which can be compared. Okay, the n equals 1 model is also really interesting. So if I have one real scalar and one Majorana fermion, they can actually be related to each other through a supersymmetry. And concretely, this means that this model has a Yukawa coupling and a scalar quartic coupling that are related to each other. The coefficients aren't independent. This n equals 1 model is very nice also because it's something that could be realized as living on the boundary of certain topological materials called topological superconductors, which can support Majorana fermions propagating on that boundary. So there's a possible experimental connection with this model. But from the bootstrap perspective, it's very nice because you can kind of throw all the constraints of supersymmetry into the bootstrap system and then compute some bootstrap islands. So we were able to determine delta sigma to the 6th decimal place, and also learn about delta sigma prime, see that it's clearly relevant, smaller than 3. And so this is currently the best available determinations of the CFT data of this supersymmetric model. By the way, I also wanted to highlight this because this work was done in collaboration with 2 Yale undergraduates who kind of fearlessly dove in to this project and produced some interesting results. Okay. We've also been working hard at the more general Gross-Neveu-Yukawa models without supersymmetry. So there are these ON invariant models that I mentioned earlier, involving n Majorana fermions interacting with an ON symmetry. And we now have some nice bootstrap results for different values of n. So we have an island at n equals 2, an island at n equals 4, an island at n equals 8. Their locations can be compared with the estimates from the large N expansion, which is this dashed line, as well as estimates from a method called the epsilon expansion. Currently, the bootstrap is really the best available method for learning about these theories.
Is there a reason for only looking at powers of 2?
Not really. We've focused on these powers because that's where other results were available that we could compare with. But there's nothing stopping us from filling in the other values of n. That's something to do in the future. Okay, here's a table of results, but let me not dwell on this too much. Okay, one thing to say is that to compute these bootstrap islands, we have to impose some gap assumptions in the spectrum. We have to assume that delta sigma prime, the next operator above sigma, starts at some value, and delta epsilon prime starts at some value. And some of these assumptions are kind of motivated by physics, how many parameters you need to tune. Some of them are motivated by kind of perturbative estimates, and they're on a little bit more shaky ground. And so one thing I did recently with a student here, Matt Mitchell, is compute more rigorous upper and lower bounds on the subleading operators in the spectrum. So we have upper and lower bounds on delta sigma prime, upper and lower bounds on delta epsilon prime, and we can see pretty definitively that sigma prime and epsilon prime are irrelevant operators for n bigger than 2. bigger than or equal to 2. This is kind of non-trivial because sigma prime becomes relevant, less than 2, at n equals 1, which is what we saw in the supersymmetric island. But these results help to put the gap assumptions that went into the previous plot on firmer footing. As I also mentioned, there's kind of this landscape of these fermionic models. So we've also been trying to more systematically classify Gross-Neveu-Yukawa models involving interacting fermions. So something that we've done is we've written down the most general form of the interaction between, say, m scalars and the fermions, which involves some unknown matrices R, and we found all the possible matrices R consistent with the symmetries for 1, 2, or 3 scalars. We then found all fixed points that you could see in perturbation theory. And this has revealed, first of all, some models that were previously known called chiral GNY models, chiral Ising, chiral XY, chiral Heisenberg models. These are all very interesting targets for the bootstrap that have different symmetries than the ON invariant one that I showed you before. This classification has also revealed a couple of new models that, as far as we could tell, haven't been discussed in the literature before. And so these are also very interesting models to now think about, to see if we can bootstrap them, and also to think about possible applications. And just to show you that we now have some preliminary results for a bootstrap island in this chiral Ising universality class. Okay, so where do we go from here? Well, there's still lots to do. There's a whole landscape of CFTs involving interacting gauge fields, which is very exciting to think about. So there are theories like three-dimensional QED, quantum electrodynamics. This describes the physics of materials called quantum spin liquids. There are 3D Chern-Simons matter theories. These are very interesting because they can describe phase transitions between 2 different topological phases. In the ON vector models, I showed you some small islands, but we haven't even yet mixed in the global symmetry current or the stress tensor into these studies. That's probably going to be able to make these results even more precise. We're also starting to explore higher point functions, 5-point functions and 6-point functions, and to see if there's some information we can extract from them using bootstrap-like methods that's hard to access from the perspective of 4-point functions. On the longer term, there's some interesting targets like the conformal window of 4-dimensional QCD. If I have a theory of quarks and gluons like in the real world, but I start varying the number of quarks, varying the number of gluons, for some values you have confining behavior and you see bound states like protons and neutrons. For other values, you see conformal behavior at long distances. This is exactly when this happens has been a long-standing open question, and it's a natural target for the bootstrap. There's also supersymmetric versions of all of these theories that are interesting to think about because there are often other powerful methods, theoretical methods available to place additional constraints on supersymmetric theories. On the other side, we've started understanding analytically how to think about the bootstrap equations, but it's clear there's a lot more to do. There are interesting analytical expansions that have been developed. Large spin expansions, large charge expansions, large dimension expansions, these inversion formulas I mentioned. I think something that's really exciting is to kind of take the analytical insights and lessons that we get from these methods and figure out how to incorporate them into a more powerful kind of hybrid numerical analytical bootstrap program. We're learning lots of things about asymptotic behavior of the spectrum in different directions. It would be great to put that into the numerical study. I also didn't have a chance to mention that there are lots of other bootstrap programs out there. They have many kind of structural similarities, but the details are often different. But there's a bootstrap for scattering amplitudes, which can tell you about gap theories. There's a bootstrap for effective field theory coefficients. There's a bootstrap for matrix quantum mechanics. There's a bootstrap for 2D CFTs called the modular bootstrap. And these all live in kind of a nice continuum with some problems in pure mathematics. The sphere packing problem is like a bootstrap problem. The problem of bounding Laplacian eigenvalues on hyperbolic manifolds is a bootstrap problem. There's a problem in mathematics called subconvexity bounds, where you bound cousins of the Riemann zeta function. This is really a fruitful arena where you can exchange ideas between these different bootstrap programs, bring insights from one into the other, and it's a really great way to make progress. Finally, I want to leave you with just a couple plots of some mysteries in the bootstrap. Okay, so we've computed some bounds using the bootstrap, and we've seen some interesting kinks in those bounds, and we have no idea what they correspond to. Okay, so here's a bound coming from fermion 4-point functions in 3D CFTs. We see a very prominent, interesting-looking kink in the bound. We have no idea if a theory lives here. There's a similar story in 4-dimensional CFTs with minimal supersymmetry, called n = 1 supersymmetry. We compute a bound. We see this kind of kink in the bound. We can conjecture that a theory lives up in this kink, but we don't know what it is. I just wanted to highlight the potential here for the bootstrap as a discovery tool. We can use it to discover new theories that we didn't know existed previously. And we have some examples that could possibly be new discoveries that are worth studying more carefully. I just wanted to also give a shout out to something I'm working on now with some students here called studying CFT moments. So we're thinking about ways of reorganizing the CFT data into moment variables, which tell you about properties of the distribution of contributions to a 4-point function. And these are basically, you take the expansion in conformal blocks times coefficient squared and insert some extra factors of delta to the k. These moments are kind of nice because, first of all, we've been able to get nice analytical bounds on the moments in the large dimension limit. And also, you can set up a numerical problem for the moments. And so, for example, the first moment can be interpreted as the average scaling dimension contributing to a 4-point function. You can compute numerical lower bounds on that first moment, and you see that it has some interesting kinks in it. We're still trying to understand what these are. This could be another place where, by reorganizing the bootstrap in a different way, we see some structure popping out, which is telling us about some new theories, perhaps some new theories that we didn't know existed before. With that, I just wanted to say that we started to map out some islands in the map of the world, but I think with more work, we could really create a detailed map of all the space of conformal field theories. Where are all the islands? Where are the continents? And in doing so, we might discover a new world. So thank you for your time.
So we have time for a few questions.
I guess it seemed like your bootstrap islands all had kind of different shapes. They were like oblong on different axes.
Yeah.
Does that tell you anything about that theory? Kind of what the island looks like, or is that just a product of how you're doing bootstrap?
Yeah, no, I mean, it is telling you something about like solutions in the vicinity of this theory, and these islands are kind of the intersections of curves going in different directions that are all carving out this shape. And those curves might correspond to different families of solutions to crossing symmetry. And so, yeah, the shape is telling you something. It's a little hard to tease out exactly what it's telling you. But it's not, it's not just numerical noise. There's some real structure there.
I apologize. Can you go back a little bit in your slide? I'm trying to remember the slides. It'll be keep going a little bit. It was when you were plotting the one more, sorry.
Okay.
No, three more. No. Other way.
Other way?
Right.
Right?
One more. Here.
This one, yeah.
Yeah.
Okay, good.
So in these plots, we see that the data points are matching the curve well, but then once we get to the, I apologize, what is the x-axis rate, h bar?
So it's h bar. It's closely related to the spin of the operator.
Why is it diverging so significantly once you're getting to about 47? Or like, why are the error bars so much larger all of a sudden?
Oh, good. Yeah. So the black points are the the numerical data from this numerical bootstrap where we extracted these zeros. So what that's telling you is that this approximate solution that we're reconstructing is kind of breaking apart once we get to sufficiently high spins. Okay, so it's missing, this approximate solution is kind of getting all of the leading operators up to spin 40, but it's missing operators higher than that. So that's basically what it's telling you. So you get some sense for where you're correctly reconstructing the spectrum and where it's breaking down. Yeah, Talia.
In the Ising model case, at one point there was an island and a continent, and I was wondering,
Yeah.
was the continent ever ruled out, like by the stress tensor analysis, or is that technically still allowed, just not where the solution ends up being?
Right. Yeah. No. There is still a continent over there. It kind of recedes a bit, but when you add these more constraints, no, you can't. You can't completely rule out every other part of parameter spaces. And in fact, there are other solutions that live out there compatible with the assumptions that you put in. So you always have to think carefully, like, you put in some assumptions to the bootstrap and it's allowing some theories and disallowing other theories. But, a lot of times there are still some solution, some other CFTs that you weren't even thinking about that are still allowed by your assumptions. Yeah. Cedric.
So in the beginning, you mentioned that these bootstrap theories are all informed by symmetries and mathematical constructs. Right?
Yeah.
Do people ever sort of add in like experimental results to help constrain the theory even more?
Yeah, that's a game you can try to play. You can take input, let's say you experimentally measure one exponent or one scaling dimension pretty well. You can input that into the bootstrap and then try to predict other things. It's definitely a game one can play.
Is that just like, is it harder somehow to do that, or? Like precise, maybe?
Yeah, you're always not sure about are the error bars on the thing you're inputting on solid ground or not? Ideally you're just predicting everything from the bootstrap, but maybe that's not always possible. So, for example, in one of these examples I mentioned of this 3D QED, which related to quantum spin liquids, that's a case where, we've tried to play some games where we input one measured scaling dimension and see what else we can predict and see whether it's self-consistent or not. And so in cases where you can't easily get a bootstrap island, that might be the direction to go.